In this video, I'll demonstrate how setbacks and overshadow controls are applied to a lot within an established urban neighbourhood, where solar access is often a sensitive subject for neighbouring property owners. We'll examine how these controls impact the design response for a new home. So first, we'll establish the front setback, which in this scenario is the average of the setbacks of the adjoining properties. Next, we'll determine the side setbacks, which can vary depending on the lot width. Narrow lots permit building to both boundaries, whereas wider lots require setbacks to both boundaries. And for lots in between, building to one boundary is permitted, which applies in our case study. Then to conclude, we'll prepare shadow diagrams and check the solar access of an adjoining property before and after the new home is built, checking that the living area and the private open space receive the minimum required sunlight. Thanks for tuning in to Design Construct, where we deep dive on topics covering design, planning, construction, and many more, helping homeowners set up for success. So this inner city lot is about 10 kilometres or 6 miles from the Sydney CBD. This suburb, like many inner city suburbs, is gradually undergoing intensification, with rear extensions, second story additions, and full knock rebuilds. This intensification comes with a need to control the impact on the amenity of the neighbourhood, where good amenity is often linked to plenty of access to direct sunlight, but can also mean maintaining consistency with the scale and the siting of new houses within a given streetscape. So first, we'll establish the front setback. The planning policy applicable to this lot sets out requirements based on the lot's area. The lot's area is shown on the site survey, or can be measured roughly using a geographical tool online. Our lot has an area of 380 squares, therefore the building's front setback must be the lesser of 4.5 metres from the front boundary, or the average of the nearest two properties within 40 metres. In this scenario, the two properties to the south were selected to be representative of the front setback, and the average of their setbacks applied to the subject site, which is about 6.5 metres. The property to the north was not used because it was built in more recent times, and it is a townhouse development, and it is not considered representative of the street's characteristics. This is an important distinction to make early in the design process. It has the effect of pushing the front setback several feet deeper into the property. If design had progressed using an incorrect setback, this would likely lead to abortive design, attracting more time and cost during early design phases. Now let's establish the side setbacks. Planning policy sets requirements based on lot width. Our lot has a width of 9.2 metres, a dimension provided on the site survey, but can also be measured using geographical tools online, however with limited accuracy. Once this is known, we look up the applicable setback, which is 900 for the first 5.5 metres of height, then increases at a rate of 1 in 4. Now, because this lot is less than 12.5 metres wide and there is no building within 900 on the adjoining lot, we can build to one boundary, to a height of 3.3 metres, after which the 900 setback applies. These setbacks are often shown on section drawings, helping illustrate how the proposed new building position is compliant. Another key constraint on this site is to maintain at least one car space, which must be located 1 metre behind the front building line. So we'll represent this car space adopting the minimum standard dimension of 3 by 5.4 metres and avoid encroaching in this zone. With the front and the side setbacks established, spatial and concept planning can progress, making sure that the proposed building envelope remains inside the building location zone and heights are measured relative to the existing natural ground level. Building height at any given location is measured from the natural ground level directly below, which will be recorded on the site survey. Now onto shadow diagrams. We'll evaluate two solar access controls. The first control checks whether a minimum of 2 hours of solar access is maintained to the main living room glazing between 9 AM and 3 PM on the 21st of July, being the winter solstice when the sun is at its lowest altitude. To evaluate this criteria, the existing and proposed house must be modelled in 3D, as well as the adjoining property, and care must be taken to capture fenestration, the eaves, gutters and ridge lines with good accuracy, and the project must be oriented relative to true north. The project's location is selected, the day and time is set, and shadows are rendered and evaluated. Then we examine the living room glazing during the hours of 9 AM and 3 PM. In our example, a portion of glazing is impacted from the new house in the morning and in the afternoon. However, there is no change to the clear story windows, therefore this control is satisfied. The next control relates to solar access to the private open space. We need to maintain 2.5 hours of solar access between 9 AM and 3 PM to at least 50% of the private space. Again, shadow diagrams are rendered at 9, 12 and 3 p.m, before and after, by this time from a top view, allowing the private open space to be examined. The extent of the shadows are unchanged, therefore this control is satisfied also. Solar access assessments can be much more involved than this and often require shadow diagrams at hourly intervals to better understand their true impact. So that brings us to the end of this video, folks. If you want tips on fundamental passive design techniques, check out this video. Thanks for tuning in to Design Construct. Please hit the like and the subscribe button, and I'll see you at the next one.